Right. This is a dirty introduction to relations and functions for linguists. So we'll start with relations, then we'll talk about functions. So a relation is a set of ordered n tuples. And you might ask, what is an n tuple? So let's talk about that in a way that's a little bit more casual. So maybe I won't use that much of the screen, but we can use this much of a screen. An n tuple is just saying how many items are in like a pair or triplet. So you might have examples of, say, two tuples, and this can be an ordered pair between two objects. So let's say we're talking about something in numbers, like a less than two tuple, for example. You might say that one is less than two and put them in that order. So this is very mathematical. Or let's say we're talking about a relationship like where you have two people that love each other, or maybe just one person loves another. So let's say John has a crush on Mary, then we could say John, Mary is a pair. And what matters is the order. So the order John, Mary is not the same as Mary, John. So this is how it differs from a set. So these can be elements in sets. We can also extend these to say three tuples. So if I want a three tuple, then I'm looking at three objects. And just to be very brief, it would be like saying A, B, C, where A is the first object, B is the second, and C is the third. So the order matters. So in linguistics, we use these relations and n tuples to talk about different types of things. Like one of those would be transitive verbs. So let's say, for example, that I'm talking about a transitive verb like hates. And maybe I have this universe where, I don't know, this person named Jody, she just hates everybody. So when I talk about the verb hates, I can think of it as being a bunch of different pairs of people who hate each other. So there's like this order. There's the person who does the hating, so we'll call them the hater, and then we'll call the people who are being hated the hatees. So let's say, for the sake of this argument, we have people, and we only have, say, Jody, Mike, and Carol in our set, and we're thinking about all of the haters. And we said that Jody hates everybody, but not herself, because Jody's a bit of a narcissist. So Jody is in a pair where Jody hates Mike. So this is our first element of our verb hates. And then Jody also hates Carol. Nobody else hates anybody else because that's how we're setting this up. So this could be the set hates. So we can think of verbs with transitive verbs, ditransitive verbs, even intransitive verbs. We could have one tuples, where we just have one object. So yeah, we can use verbs when we think about relations. We can also think about nouns and adjectives as relations. So what about ditransitive verbs? Well, let's say that we have a verb like sends. We know there's going to be an English equivalent to sends, like how we normally use it in a sentence, where we would say X sends Y to Z. And we know these are different parts of speech. We have a subject, we have a direct object, the thing being sent, and we have an indirect object where it's ending up. So we could think of sends as being a bunch of three tuples. So we could write this as, say, the sets of subjects, then direct objects, then indirect objects, where the subject sends the direct object to the indirect object. So this could be how we think about this set. So let's say Jody is a human driver. We'll use that term for the YouTube algorithm. And Jody is driving Mike to Carol, but Jody's sending Mike to Carol. Then we could say that this is the three tuple where we have Jody sending Mike to Carol, and maybe that's the only thing that's happening here with sending. So this would be our set here. So, in terms of what relations are used for, most of the time they're just used for verbs. But you can think of other relations too, like with a determiner, possession. Mike's friend. We have a relationship between Mike, the owner, and friend, the thing being owned or the thing being possessed. So that could be another thing that relations are used for. Now, relations can be categorized into several different types, or they have different properties. So you can have reflexive relationships. So you can think of these as actions where, let's say, you have a person A, and whatever the action is, A is related to itself. So maybe you would think of a verb or property as being is the same height. Now, this is kind of weird, but when you think about it, let's say you have a person, we're going to bring Jody back. Jody's our protagonist for today's journey. Uh, every person is always the same height as themselves. So if Jody is a person, that means that Jody is the same height as herself. So in our relation, what we would see is that every individual in the first part of the pair would be related to themselves again in the second part. If this property holds for every single member, then we say that a relation is reflexive. If we have something like symmetry, what this means is that if we have two objects A and B, and A is related to B, then we're going to have B related to A again. So the example I like to think of this is a sibling. So in other words, if I am a sibling of my sister, then my sister is a sibling of me. If Jody is a sibling of Mike, then Mike has to be a sibling of Jody because that's the way the language is structured. So basically what we're saying here is let's say that we have the pair JM in a relationship. What this is going to force, if it's symmetrical, is that M and J are in a relationship with each other too, in that order. So in other words, if A is related to B, B is going to be related to A, and is a sibling of is a really good um, example of this. Transitivity is a little bit more interesting. So this is when we have three objects, A, B, and C. And suppose A is related to B, and B is related to C. So we'll set up a relationship. Actually, we'll do that after. What transitivity says is if A is related to B and B is related to C, then A is also related to C directly. So it's kind of like taking a shortcut. So I like to think of this as a relationship like is older than. So let's say we have three people here. We have Jody, we have Mark, and we have Carol. I think Mike has changed his name to Mark. That's okay. Jody is 83. Mike or Mark is 51, and Carol is 27. So we know in our relation here for older than that Jody is older than Mark. We know that Mark is older than Carol, and because is older than is a transitive relation, we also know directly from this fact that Jody is also older than Carol. So in other words, if the first two hold true, J is related to M and M is related to C, then we also have this shortcut as well where J is related to C. And older than or taller than is a really good way of showing that. Now, the last one that we'll talk about is the equivalence relation. And this is a little bit special. So this is a relation that is reflexive, it is symmetric, and it is transitive. So it's all three of those things. Now, what this looks like, we'll just do this with three different elements here. We'll do A, B, and C. What this means is that everything is related to itself by the symmetric property. If we have a relation from A to B, then we're going to have a relation from B to A back. So we might have something that looks a little bit like this. And then it's also transitive. So if A is related to B and B is related to C, then A is related to C as well. And What we get from this is equivalence. So this is why we use words like is the same, and then you could put a property as. So is the same x as. So is the same height as. Is the same age as. Is the same weight as. In other words, everything's equivalent to each other. So this would be a case. Let's talk about weights here. So despite the big age difference between Jody, Mike, and Carol, they all happen to weigh exactly 50 kilograms. And if you're like me and you don't use kilograms for weights, we can give this an actual number. We can say they're all 110 pounds. So if we have a relationship saying is the same weight as, then all of these people are related to each other. They're related to themselves, and this is transitive too, because they're all going to be the same weight as each other. So these are the different properties that relations can have. And this will be useful when talking about determiners as well in the future. Now we'll talk about functions. So we need to talk about relations first because functions are special types of relations. Usually how we think about functions is like a map. So we have a set A, we have a set B, we have a bunch of different elements in A, we have a bunch of different elements in B, and what a function does is it takes an element in A and pops out an element in B. So this is a function. Let's call this x, let's call this y, and we'd say that if x is applied to x, then we get y out. So this is what you get your notation for f of x is equal to y. You've probably seen this in math, but in linguistics, we do very similar things. And one example I like to give is GPA assignments. So imagine that what we have are a list of students, and we have a bunch of different GPA values. So what this is going to be is this is going to be a function from students to GPA. Now, the requirements of a function is that everything in our left box, our first set students, has to be given something in our right set. So every x in students has to have some y in GPA. So I'm just going to label these students as 1, 2, 3, and 4. And let's say there's different GPAs. So we have 4.00, we have 3.50, we have 3.00, 2.50, and we could just keep going on. We'll just use these for examples. So we can have a function that says, okay, for each student we have, what GPA do we get? So student 1 has a GPA of 4. So that means that if I put in student 1 into my function, what I'm getting back is the GPA of 4.00. Maybe student 2 has a GPA of 3.00, and student 3 also has a GPA of 3.00, and then 4 has a GPA of 3.50. So we could do another example. If we put f of student 2 in here, we would be getting 3.00 back because that is their GPA. We could also think of a function being like from IPA sounds. So you can think of IPA characters, and then you could think of sound descriptions. So, for example, imagine we have an IPA character like p. Well, this sound has a description, so we could have a function that maps the IPA sound to a description. So if we give a function f, we put the sound p into it, our output might be a voiceless bilabial stop, for example. So you put something into a function, it gives you something back. The thing with functions is that if you put in an input, it has to give exactly one thing back. That's the second unique part of functions, that everything in our IPA should have a description, and each of those descriptions should be unique. In relations, Jody might hate Carol and hate Mike, so Jody hates two different people. But if we're thinking about functions, we can't put in Jody and get two different people back. We need to be able to get exactly one thing back. So Jody hating Mike and Jody hating Carol wouldn't qualify as a function. Yeah, it could be a relation, but not a function. So those are two more real examples of that. And just like relations, functions have different types and properties as well. So I'll do some abstract pictures for these. One is one-to-one functions. So I'll just draw something like this. What a one-to-one function says, maybe I'll put four things in our right set, is that for each object in our first set, it has to go to a unique output in our second set. So something like this would be acceptable if we have 1, 2, and 3 going to A, B, C, and D, because each of our outputs is unique, it's one-to-one. Now, an example of something that is not one-to-one would be something like this. 1, 2, 3 going to A and B. So we could do this, this, and then 3 goes to B as well. And because we have this case where both 2 and 3 are going to the same thing, this one is not one-to-one. In other words, one-to-one is about the uniqueness of our values, our outputs. Onto is a little bit different. What onto is saying is that when we take a look at all of our outputs, every single possible output is given. So let's say we have 1, 2, and 3 here, and this goes out to A and B. As long as all of A and B are covered in our outputs, it is on 2. So because, yeah, 1 goes to A, 2 goes to A, and 3 goes to B, because at least something goes to everything in A and B, it's on 2. So an example of something that is not on 2 would be something like this. So we have 1, 2, 3, have A and B, and now imagine that when we put either 1, 2, or 3 in, it all goes to A. So because we have this element B that isn't an output for anything, this is not going to be on 2. So in other words, when you're thinking about functions, sometimes it helps to draw these out if you have a finite number of elements and just check to see, okay, is every input going to unique output? If so, it's one-to-one. And if we're on 2, is every element in our input, when we add them all up, is it covering all of the possible outputs? If yes, it's on 2. And then you can work through those examples. There's not really a nice way with language to pick out specific things here. This is more so properties that you would check after for specific types of functions that you're given. Now, the last important thing with functions to talk about is the characteristic function. Now, this is a sorting function, and we can think of it like this. It's a function that sends objects to one of two things, true and false. So what this means is that if we have two sets of things, the only possible outputs that we're getting are either going to be true or false. So I like to think of characteristics as sorting functions. So for example, we might have a sorting function that asks, is it a vowel? So we can think about all of our possible inputs as English letters, so A, B, C, D, E, F, and G, and so on. And what a characteristic function is going to do is going to ask the question, is it a vowel? If it is a vowel, it's going to sort it into true. So yeah, A and E are vowels, it goes to true. And everything else in our set is not a vowel, so it's going to map to false. So what these characteristic functions do is they sort our sets into essentially two halves. We have the elements that have some specific property, and then we have elements that do not have that specific property. So these are all of the trues in the properties, and these are all of the falses in the not properties. Now, the term for this is called a predicate. So this does relate very closely to predicates in linguistics. Like you can think about a verb like, let's say, sleeps. And we can say this is a function. So what sleeps is going to do is, let's say you give it a proper name and you ask, is James sleeping? Well, if it's true, yeah, it's going to pump out a true value. So we can say that James is a sleeper. But if we ask sleeps and we're asking about our good friend Jody, we haven't heard about Jody's other hobby yet, but she is in fact a serial killer. She does not sleep. She's too busy planning things all day. So this is false. So, yeah, we can think of predicates in linguistics as being characteristic functions in natural language. At least this is how we can start with model theory when we think about truth conditional semantics, and then we might have to do some modifications for, say, lambda calculus when we get there. So this was a pretty quick and dirty intro. If you need more information on relations and functions, you can check out my discrete math series here on YouTube. There's playlists in discrete math 1. But in terms of understanding enough for linguistics, this is really all you need. Taught semantics a lot, and if I were to redo my course over and over again, this would be how I start to teach it, more focusing on the language side and just the general concepts rather than all of those nitty gritty details. So if you have any questions, leave them below. Like, comment, subscribe, all that fun stuff, and I hope to see you in the next one.